Hello and welcome to Workshop 8. What we're going to be talking about today is limits and Taylor series. And mathematicians traditionally love limits because they help them prove why calculus actually works. But what about engineers? We're not worried about proving that calculus works. We're more worried about actually using this stuff in real life. So how do we use it? Well, let's take an example. Here's a real one. If we, sorry about that, my drawing skills are still a bit dodgy. If we have a graph, and on this side we're going to put drag, and on this side we're going to put velocity. Now, what happens is that there is a nice little curve, and then it will suddenly spike up to infinity at this point here. And in case anybody is interested, this is the speed of sound. So at the speed of sound, the amount of drag, the frictional force, suddenly blows out to infinity. And that turns out to be a limit. And mathematically, we can model it as a limit. Now, in reality, of course, this doesn't actually blow out to infinity, and that's because in reality molecules and atoms have a physical size, and the limit, this model is based on the fact that atoms and things are infinitely small. So that allows us to actually draw it like this, but at this point here, that is going to be our max force, or if you're in rocketry, that's called max Q, maximum dynamic forces. So there's a limit there. Another limit that I was doing personally in my research, this is going to be the displacement, let's call that Z, and this is going to be the frequency. So if you've got a car suspension system, a wheel going up and down on the ground, there's a frequency with which it's bouncing. And so the amount of displacement, the amount of bounce that you get on your car wheel, so it starts off, and at a certain frequency it blows out. Then it tapers off, and then at a second frequency, there's a hop. So this is the resonant frequency of your system. And if you're talking any system, whether that's a bridge swaying or a building swaying in the breeze or something, this resonant frequency here represents the limit, is a mathematical limit. You also get limits when things approach the speed of light, as I said, suspension units. In electrical systems, for example, when you hit a resonant frequency, a lot of electrical systems have a resonant frequency, especially when you run a resistor. If you're running a resistor, a capacitor, and an inductor network, that will have a resonant frequency. And resonant frequencies are used all the time for things like radio receivers, TV receivers, all sorts of stuff. If you were to plug that, the amount of, you get a reactance, but you get a transmittance, the amount of signal for frequency, same thing goes along, nothing goes through, comes through. There's our limit right there. So limits do actually turn up in all sorts of places, as I said. So how can we deal with limits? Sorry about the fact that I look like a... Now, the easiest one is if we have a limit, and let's say x plus x squared plus 2, and we want to find out the behavior of that as it heads towards some number, as it heads towards 2. Now, we can plot a graph. As that approaches 2, we can, at 0, it's going to be 2. At 1, it's going to be 1 squared, it's going to be 3. At 2, it's going to be 4. Now, at 5, it's going to carry on. But what we want to find out is the behavior here. We can plot graphs, that's it. Or we can plug numbers in. One of the techniques as engineers we use is we just plug numbers in. We see what happens. I plug a number into that equation, then I end up with 2 squared plus 2 equals 6. Done. We have a number. So if you end up with a finite number, done, easy, real easy. But what happens if we have a more complex problem like limit, it's just of, I don't know, 1 over x as x heads towards, I don't know, 0. And we're going to come from the positive direction, so we're going to come from the right-hand side. Now, if we look at that behavior, as it approaches 0, 1 divided by 0, that blows out and becomes undefined or infinity or whatever. Not so easy to deal with, but we know that that blows out. And if we plot that on a graph, as it goes towards, as we're approaching from this side, as we come and it blows out and it actually becomes asymptotic on that value. That's cool. But so often limits will blow out to infinity, like as I said, speed of light, my suspension systems, things like that. But so we can end up with a case with a non-zero number that blows it. We could also end up with a case of 0 divided by a finite number. That's easy enough, it just goes to 0. But what happens when we end up with more complicated cases? Now, if we take something like lim of 4x minus 2 over 6x squared plus x minus 2, and we want to find that value as it approaches half. As that approaches half, what's the value go to? Well, let's try an engineering approach. We just plug the numbers and see what happens. 4 times half is 2 minus 2. That's going to give us 0. Okay. Okay, well, let's try the bottom. So if we put in a half squared, that half squared is 1/4. 6 times that is 3 over 2. Plus half is 4 over 2. 2 minus 2. We end up with a case of 0 over 0. Now, what is 0 over 0? Because we're taught 0 over anything is equal to 0, and anything over 0 is undefined. So what's that equal? And you better ask Sean, he's the mathematician. But the important thing from an engineering perspective is this can still have a value that is not 0. And so we have to go for plan B. And there are 3 basic approaches that we can do. We can approach number 1. We can factorize. Find out, see if we can find it now. We can 2 expand anything in brackets. 3, we can use conjugates. So looking at this equation here, I could possibly factorize the bottom. So looking at this, I can factorize this. There's nothing to expand and there's no reason. So if I'm just doing this, I now got the lim. I'm going to factorize that. So what do we end up with on the top? Well, we can pull out common factor of 2 on the top. 2x minus 1. And on the bottom, we can, oh no, that's going to be 2x, isn't it? Because 2 times 2 is 4. And on the bottom, we pull out 3x plus 2. This is using our equation times 2x minus 1. And you'll now notice that there is a common factor on the top and the bottom. They cancel. So now we have the limit of that as that approaches half. So we've now got 2 over 3 times half plus 2, which is equal to what? 4 over 7. So now in this case, this number up here equals 4 over 7. So we can also do things like this with expansion. If we've got 4 plus x all squared minus 16 all over x, and we want to find that as it approaches 0. If we just stick that all in, if we stick 0 in all those values, it equals 0. But if I expand the top, now we end up with 16 plus 8x plus x squared minus 16 all over x. We refactorize that now and we end up with, well, they cancel. So we end up with 8x plus x squared over x, which is equal to x times 8 plus x over x. They cancel. So now what we're trying to do is we're trying to find out the limit of this system as it approaches 0. So 8 plus 0 equals 8. So again, this is a case where we had a 0 over 0, and it gives us an actual finite number. And the last quick one that we'll do, let's clear all that, is, I'm not going to do the full example because I look like my doctor's handwriting is really crazy. Sorry, that goes to 7. If we put in here square root of x plus 2 minus 3 all over x minus 7. If we stick the numbers in, x goes to 7. So 7 plus 2, 9, square root 3 minus 3, we end up with 0 over x minus 7 is also going to be 0. But how can we actually solve this? And there is a trick. And what we do is what we take the conjugate. We multiply, we put this whole lot in here, and we multiply this by square root of x plus 2. But instead of adding 3, we're going to take the opposite function, plus 3. And mathematically, what you do, if I multiply the bottom also by x plus 2 plus 3, mathematically that's true, because this divided by that is 1. So basically we're effectively multiplying by 1. Anything multiplied by 1 is itself. And if you chug through all of that maths, if you multiply that bracket by that bracket and do that by that, you should end up with limit of, what's that, x plus 2, sorry, plus 2, it's not, no. Sorry, wrong one. If you chug all the way through that, you should end up with one limit approaching 1 over 7 plus 2, comma, plus 3. So you should end up with 1/6. I'll leave that to you. Okay, so the basic approach, when doing all of these, and hopefully we'll get better recording equipment next week. Sorry to everybody who's had to put up with this. Is one, we plug the number in. And there's 3 cases. If we plug the number in, we either end up with a finite number, that's a win, or we'll end up with a non-zero over 0 number. That's also a win. Or we could end up with a 0 over 0, and then we have to do that 0 over 0, and then we have to do that factorize and cancel, expand, or take the conjugates. Okay, last thing, and I'll leave you to your problems and such like. What happens, let's take a problem, what happens when you, say we're doing maths and we're doing some math for our stuff, and we have to integrate something, I don't know, x squared plus some other function, which we're integrating some function, and there is no analytical solution. What I mean by that is we do not yet know mathematically how to figure out what the integral of that is. How can we actually work that out? And one of the old tricks that we used to do, and we still use occasionally, and we actually still do, is Taylor series. So what we can do is we make a function that will approximate this. And it's not 100% accurate, but it's like 99.9% accurate. And so we'll use it. I mean, the classic thing is if you're playing around with your calculator, you've got your calculator, yeah, pull in there, and we've got a whole lot of keys down here. One of those is if you push sine, let's say we're in radian 0.7, how does your calculator know what sine 0.7 is? It doesn't have the memory to store every single solution. In the old days, when I was at school, we just used to have a book, and in it, it would have sine values for 0, for 0.1, for 0.2, and you just look them up. But there's not enough memory in a calculator to do that to the precision that we need. And the answer is very simple. Your modern scientific calculator actually does a Taylor series. Because if you take sine x, and this is going to be in radians, that's going to equal, let's make sure that we got this right, x minus x cubed over the 3 factorial plus x to the 5 over the 5 factorial minus x to the 7 over the 7 factorial plus x to the 9 to the over 9 factorial minus x to the 11. And the thing is, if you choose the Taylor series right, very quickly this will approximate the value you want. So whenever you actually hit sine or cosine, sine on the calculator button, it does this equation. It actually does that till it gets to the point where it figures 12 significant figures is enough, because that's all we can display. So Taylor series are still actually used. They're an approximation. And the best approximations give a useful value within maybe 3-4 terms. Because if we do it right within 3-4 terms, we're within 98% or 99% of the actual value. But the thing you have to remember about a Taylor series is Taylor series are usually good over a range. So if you've got, I'm mortally offended by that. If you've got a graph and you've got your function doing this type of thing, your Taylor series might be good from here to here, but it cannot predict what's happening. It's not going to be correct over the whole range. Hopefully you do have one, but you can't always say it's going to be accurate if the whole range, just over part of the range. But anyway, so Taylor series have proved very useful in engineering over the years. So good luck on that. Okay, and hopefully I'll bring home a Wacom pad next week so I don't look like a toddler trying to play with a crayon set. So let's clear all that. So basically, there's a whole series of problems, limits and things. Have fun. Hopefully we'll see each other actually in person in the near future.